In this lecture, we'll talk about electron energy loss spectroscopy and energy filter transmission electron microscopy. Till now, we've seen the concepts of transmission electron microscopy, primarily seen TEM as an imaging tool. We covered the concepts on how basic images are obtained, how the TEM is operated in a conventional mode where you obtain the bright field and dark field images. Then we covered the concepts of diffraction, primarily electron diffraction, how to index the patterns and so on. And then we've seen how the physics behind obtaining a high resolution image is. We understood basics of high resolution transmission electron microscopy. Then we saw another technique called as scanning transmission electron microscopy. In STEM, we see that the TEM can be used as an analytical tool where from each pixel you can correlate the compositional information as well. We primarily focused on EDS. We've seen the effects of inelastic scattering, and we also saw that this can reveal the compositional details of the material. We've also seen the concepts of electron beam damage, how a specimen can get damaged under the electron beam, and how is it detrimental for imaging in a TEM. So primarily, we thought that TEM is only an imaging tool. Here, we'll be discussing about more modes in transmission electron microscopy, primarily relying on inelastic scattering. All the imaging concepts in physics of imaging has been built mostly around Rutherford elastic scattering expression, where we've seen the scattering cross section and so on. And we've understood the Z contrast also as a consequence of the Rutherford scattering expression. What we've not seen in detail is inelastic scattering effects, and this is what is interesting in knowing the functional properties of a material and the chemical properties of a material. So in this two-part lecture, we will look at more on electron energy loss spectroscopy and energy filter transmission electron microscopy. So what you should remember or recollect is when the electron beam is striking a specimen, we saw a diagram like this. So I have the incident electron beam and a host of signals are generated, primarily the secondary electrons, the characteristic X-rays, the forward scattered electrons. We call this the direct beam, and then we've written something as inelastically scattered electron. So this technique of electron energy loss spectroscopy primarily relies on the inelastically scattered electrons. So when you're operating a microscope at, let us say, 200 or 300 kilovolt, largely 95% of the signal that is forward scattered would have an energy of around 200 or 300 kilovolt depending on the operating voltage. But the electrons that have lost energy would actually slow down, they would get scattered at a different angle, and then if I can think of a construction where primarily I rely on the forward scattered electrons, if I can collect them and disperse them as a spectrum, I can quantify the chemical signature and the functional properties of a material as well. We'll look at how this is done. We'll primarily focus in the first part on how the construction is, and in the second part we'll look at a little more on the application. So electron energy loss spectroscopy, as you can see here, is primarily a spectral tool, and energy filter TEM, or you also call it as electron spectrum imaging, which is combined with STEM mode as well, is a sort of an imaging tool. So energy filter TEM is slightly different from electron spectrum imaging, where you can either operate the transmission electron microscope in STEM mode and from each pixel collect the EELS signal and build an image which appears similar to your EDS map, or in energy filter TEM, by simply collecting electrons from a certain window corresponding to an energy which has undergone inelastic scattering, you can form an image and understand what is inside the material. The primary difference here is the energy filtered TEM, which typically depends on slightly larger angles of scatter, is somewhat like a conventional TEM image where I'm recording the entire frame at one go and over a short exposure duration which can range from a few seconds all the way to a few tens of seconds. My image is obtained primarily on the energy which the electrons have lost and collected through a slit and an energy window, and an image is formed. So this gives you a rough idea that the STEM images coupled with spectral imaging can give you a better spatial resolution than the energy filtered TEM images. So in EELS and EFTEM, in the first part of the lecture, we will see how the concepts are and the spectral imaging part, and then in the second part we will see energy filtered TEM. Please bear in mind that this entire field of EELS and EFTEM, people have spent decades of their careers on this, and the entire concepts that are related to EELS and EFTEM cannot be covered in a single course or in a couple of lectures. So what you will see here is only a broad overview of how the signal is, what can be done and what are the applications. But this lectures would not give you a complete control on everything that can be done with these techniques. I'll only give you the avenues and you can explore more. I'll also try to keep this very brief mathematically, focusing on the conceptual details, but not going into complete specifics of various areas. There have been pioneering works from various groups. Ray Edgerton is the first name that comes to mind. The groups from France, from Professor Christian Colliers and colleagues. And there are groups from, of course, UK and the group of Professor Stadtschneider in Austria. And of course, the Professor Andrei Krivanek's group in Arizona State University. There are enormous amounts of work that has been done and lots of available literature, groups from all over the world. And what I'm trying to focus on is very minute, and there are enough resources available which you can look up and learn more about these techniques. So I'll start with a question on why do you use electrons or X-rays for imaging the composition of a material? The answer is these are characteristic signals that you get. X-rays in particular are emanating in all the three dimensions. So you can collect an X-ray from anywhere around the 360 degrees of the specimen. Whereas when it comes to inelastically scattered electrons, this is primarily a forward scattered signal which is within a range of 15 to 20 millirads. So when I want to understand the construction of how I acquire this signal in the microscope as well, typically the X-ray detector is a sort of a side entry detector which comes close to the specimen to collect the signal. Whereas you have either in-column construction or post-column construction for the EELS signal, and you're collecting it and sending the signal out of the microscope column, and you're analyzing it through different computational tools which are outside. So primarily the spectrometer which is placed below the microscope column is called as a post-column filter, and this is more commonly used in modern day spectrometers. So with that, we will look at the concepts on electron-specimen interaction again from a perspective of inelastically scattered electrons. We covered the concepts of X-rays, Bremsstrahlung and characteristic X-rays, the interband and intraband transitions in the previous lectures, and we'll see a few basic principles of EELS, why or how we get these energy loss events, how to detect them, what are the relevant experimental parameters, and we will also focus on some basics. Depending on the technique you're using or the tool that you're looking at, the conceptualities might differ from an instrument to instrument. Traditionally, there has been only one company which was manufacturing the post-column EELS detectors. It is called as the GIF, the Gatan Imaging Filter System. I will focus on what I've learnt or the sequence of operation that is done based on this particular imaging filter system. But there are now techniques from the company called as CEOS, which also makes the aberration corrector. They also make the spectrometers now with JEOL and Hitachi. They are now having commercial spectrometers which are largely post-column spectrometers as well. And GEOL and Zeiss also had the in-column filter where you could also do electron energy loss spectroscopy within the microscope column as well. So there are different modalities in which you can get energy loss signals detected, but I'll largely focus on the post-column filter methodology, which is more commonly used, and a broad sequence of what you should be doing to get or collect the EELS signal is what I'll talk on in this particular lecture as well. I'll look at a few applications, low loss or no loss spectra and also imaging. This is quite interesting when I talk about low loss or no loss imaging as well. When I'm looking at low contrast materials, particularly biological samples, sometimes removing out the inelastically scattered electrons and collecting only the elastic scattered electron signal, you can get images with improved contrast, and this is particularly useful for sort of low contrast materials or biological samples. The omega filter, which is available in systems like 2200 FS or the Zeiss Libra, predominantly can be used for this, and I'm aware that there is the sort of the Salve project which was developed at the University of Ulm. They were building a very low energy TEM coupled with low energy spectrometer. This is primarily focusing on beam sensitive materials as well. So there's a lot happening in this particular area as well. Then I'll talk about a few applications on high loss spectra and imaging. You have the energy loss near edge and also the extended filtered spectrum imaging as well. And you have the EELS fine structure and finer details as well. From here you get the functional properties of the material such as the band gap or the dielectric constant and so on. I will not go into complete details of worked out examples of these, but give you some broad images of what you would get on, or broad idea of the spectra that you can get and that you read from literature. And this is only a sort of a broad introduction or an overview of what the technique can be used for. You have to read into this and spend lots of time. In fact, some of these studies of EELS can be as detailed as a PhD study or an entire career of a few people who've spent over decades together as well. So it is, I'm sure a 2-hour discussion on EELS would not do justice to all the topics, but hopefully I'll be able to give you an overview of what the technique is capable of. So moving on, let us revisit this image where we saw the various signals that are produced. Here is a cartoon that I took from the famous text again, Williams and Carter. It is called as the companion volume because the amount of details that you can get from a transmission electron microscope are so broad that a mere course or glancing through a book would not do justice, and revisiting to the reference book always is recommended. And I'm not sure if there is a more simpler detailed version than the companion volume of Williams and Carter. That is a common source we all go to. So please go through it. The first part of the book talks about a broad overview of the microscopy technique, and this itself could be a semester-long course. And the next 3 parts, which is on imaging, diffraction and spectroscopy, cover on all the details. The structure of my course has also been primarily on a similar pattern where I cover the technique, I show the demonstration, and I try to show you some examples of how the data is after the technique is used. So we've now come to the sort of the last parts of spectroscopy and looking at inelastically scattered electrons. We've seen in the demonstration sessions on STEM and EDS imaging on how you use the characteristic X-rays. The characteristic X-rays, like I was telling you, is from a detector which comes in with a lateral entry detector or a side entry detector, and these signals of secondary electrons and backscattered electrons are primarily used in a scanning electron microscope. The Auger electrons are also used in conjunction with a scanning electron microscope as well. The visible light, you can use it with a cathodoluminescence type of a holder in a TEM as well, or a cathodoluminescence detector in an SEM. These absorbed electrons and electron hole pairs, you can measure how these recombinations can vary the conductivity or the band gap when you look at the EELS fine structure or the low loss structure. The Bremsstrahlung X-rays, like I covered in the previous lecture, are giving you a signature of what kind of a bond you have. The direct beam and elastically scattered electrons, we've seen the applications in imaging, primarily the mass thickness contrast kind of concepts that we covered. And in this particular lecture, we will look at the forward scattered electrons and primarily focused on the inelastically scattered electrons, which are collected in a spectrometer either in column or post column. When I talk about the spectrometer, you should be able to disperse these inelastically scattered electrons, which are scattered at a certain angle, as a spectrum on which the x-axis consists of the energy and the y-axis consists of intensity. And these intensities now and the peaks that you get correspond to the kind of the interaction that has happened between these incoming electron beam and the events that have occurred as a consequence of scattering. So, how do you get to know, or what kind of information do you get from these kind of inelastic scattered signal is, if I have the incoming electrons which are either at 200 or 300 electron volts, kilo electron volts, the inelastically scattered electrons typically are ranging somewhere between 50, or I would say starting from 0 all the way to 3000 eV. Primarily within 0 to 1000 eV is what you can meaningfully measure with most of the modern day spectrometers. And from this, by looking at different energy ranges, you can either get the fine structure or the low loss spectrum, or you can get at the near edge. There is something called as the EELS ionization edge, from which you can look at the idea on the valence state, or from the low loss spectra on the bonding or the dielectric response. You can get the free electron density, you can also get the band gap, and from the plasmon peaks you can get an accurate estimate on the specimen thickness. Once again, from the plasmon you can look at the characteristic ionization edges, understand what the inelastic mean free path is, and from this you can determine the specimen thickness very accurately. So, if I look at what information I have from what happens after the electron beam interacts with the specimen, is the data I collect that is forward scattered can be thought of as a cube, and if I look at how the energy loss is over the z axis, this is just a conceptual sketch that is shown. If I look at the electrons that have not lost the most energy, that is pertaining to the so-called zero loss peak area, and specifically when there are some ionization edges corresponding to specific elements and the transitions that happen with regard to these elements, whether it is let us say a copper L23 kind of a transition, or let us say a nitrogen or a carbon related transitions that happen, you have specific ionization edges which look like these triangles, and once you exceed a certain critical threshold energy, you get these specific ionization edges. So, you can have a sort of a window around this and form an image with these specific electrons which have undergone an energy loss, and that is called as energy filtered TM imaging. And like you are collecting a spectral image when you are doing STEM with EDS, from each pixel when I am rastering, if I collect a three-dimensional spectrum from every pixel. I can build a data set, and I think I mentioned in one of my earlier lectures there is something called as Hyper Spy, which you have an open source Python based library thing which you have. A lot of data analysis of the three-dimensional data sets is also being done with this. You can collect enormous amount of information across this entire energy range from every pixel with which you get the stem image as well as a parallel EELS signal. So this is called as parallel EELS spectral imaging. Depending on which microscope manufacturer you are looking at, there are different terminologies with which you can collect this image. Essentially, the idea is from every pixel for which I collect the image, I am also collecting the entire data cube, which consists of the composite of all these energy related information as well, which is undergone inelastic scattering. So with this, if I look at how the spectrum or the signal looks like when I disperse it through a spectrometer in an electron microscope, a typical EELS spectrum looks like this. On the x-axis, I have the energy loss, and on the y-axis, I have the intensity. When I have the core loss or low loss or sort of no loss kind of a region, if I see that this particular point is corresponding to 0, which is where primarily my forward scattered direct beam is, this particular window here corresponds to largely the elastically scattered electrons which have not undergone energy loss. This is called as the EELS zero loss spectra. The zero loss peak that you get in electron energy loss spectroscopy is the most important one, which is used for calibrating the spectrometer as well, and also used as a reference based on which, in comparison with the zero loss spectra, whatever signal I am collecting from the forward scattered electrons, when I disperse it on the spectrometer, how much energy loss has these particular ionization edges undergone in comparison with zero loss spectra is what gives me a signature of which element this corresponds to. So if I look at the low loss spectra, I am typically looking at 0 to 64 or 0 to 128 or 256 EV, and primarily in this window of 0 to 50 EV, I get complete information on the events such as whatever intra-band transition between the conduction and the valence bands happens, or whatever bulk plasmon changes are happening, which gives me a signal of the bulk plasmon events, and from this particular bulk plasmon signal, I can determine the inelastic mean free path, and I can also compute for the specimen thickness as well. So these are the typical signatures I get from the low loss spectra. And when I look at this signal, let me quickly erase these content again. If I look at the ionization edges and the EELS near edge structure, I can get information on the bonding and the chemical signature of whatever elements are present in. Now, the beauty of EELS is I can use different kinds of entrance apertures for the spectrometer. I know at what angle the forward scattered electrons are entering, and if I know the thickness of the specimen, whatever electrons that have undergone inelastic scattering under this peak are forming a peak of this height. You can actually integrate this from this area under the curve. You can quantitatively get an accurate signature of how many number of atoms have given this kind of a signature. And what is more interesting is, from an ionization edge, depending on whether I have a so-called white line peak or whether I have a kind of a sort of an extended peak, and the shape of the peak. I can also see, analogous to the information you get from XPS, you can get complete chemical signature from different elements and what kind of valency you have in that particular compound as well that you are investigating. So this is enormous amount of information that you can get from electron energy loss spectroscopy. So if I look at an example, so what you saw here is conceptual sketch of how these EELS signals would look like, and what you see here is an EELS low loss spectrum recorded. I wouldn't call it low loss because I'm dispersing completely from 0 to 500 EV in this particular case. So in the spectrometer, this is essentially a CCD camera, or nowadays people are also using a CMOS based camera as well. You record typically on a 1024 EV window here. Depending on how the energy dispersion is, I can record within specific ranges. I can choose to record only within this low energy loss region, which is from typically 0 to 50 or 0 to 60 EV, and I can focus only on information that I get within this particular window. Or if I have elements which have characteristic ionization edges within 200 to 300 or 400 to 500 EV, I can only focus on signal I collect in this particular energy window. So the strength of this particular technique is on the same specific spectrometer. Once I collect the low loss spectrum and I look at how the zero loss and the plasmon peaks are, and I get an idea on the thickness of the specimen, from this information I can next focus on specific energy windows where I know how my ionization edges are. And when I talk about ionization edges, there is something called as the EELS Atlas. It was by Professor Andrei Krivanek and his colleague Anne. With these, they have done a compilation of almost all the entire periodic table of elements. So you already know beforehand, and this is now stored digitally on modern day spectrometer software as well. You know that, for example, if I'm looking at carbon, I need to look at somewhere around 280 EV. If I'm looking at oxygen, 532 EV. If it is copper, 720 EV, and so on. So I know that element wise, if I want to collect specific near edge spectrum, you start with looking at the low loss spectrum first, and then you focus on specific energy windows, and then get meaningful quantitative data as well. So if I zoom in closely here, if I look at somewhat like the energy window of 100 to 250, there is the aluminum edge here, but because I have a strong signature of the bulk plasmons, I cannot see the spectrum here. So if I want the aluminum signal, I would want to focus on this particular energy window such that the events corresponding to the ionization of aluminum are more prominent, and I can record them on the EELS spectra. So this is how your realistic EELS spectra would look like, and from the information you have under the specific ionization edges, you can start quantifying approximately, or I would say to a very good beyond 98% accuracy, from how many atoms are you getting this kind of a signal. So this is an extremely powerful tool, provided you know what the thickness of the specimen is. So again, quantifying this and getting quantitative data from EELS takes a lot of effort. There are a host of parameters that you need to know: the collection angle, if I'm scanning from different areas, the illumination conditions should also be exactly the same. So if I want to do quantitative comparison from two different regions of a specimen, I should see that all the illumination details are actually consistent and the specimen thicknesses are consistent, and only then I can actually get meaningful quantitative EELS data. So please, so when I talk about what the technique can do, it might be very appealing that you want to jump into getting this kind of a data, but please remember that it is not that straightforward. So if I look at, for example, let me erase this again, the ionization edges from oxygen and manganese. In the previous case, I was looking at aluminum, which is around 76 EV if I remember correctly. This was done already some time ago. But if I look at oxygen, it is around 530 and manganese is around 630. And somewhere here you would have copper and iron as well. So you can choose which range of energies you are dispersing on the spectrometer, and you can successively start collecting the data. I can also choose to do this in the spectral imaging that we collect for STEM EELS, and you can collect the entire window. But again, if you look at how the shape of the energy loss spectrum is, from 26,000 counts for the zero loss spectrum to around 4,000 counts for somewhere around aluminum window, depending on the exposure time and the window that I am looking at, the meaningful signal that you collect from ionization edges, the number of counts would drop down. So you should be very careful in how you plan in collecting your EELS signal depending on what kind of information you want to collect. Okay. So now let us try to understand how the construction of EELS spectrometer is, just the conceptual construction of the thing, and how we obtain the energy loss signal from a transmission electron microscope in the upcoming slides. So how do we obtain the energy loss spectrum? If I look at the classical spectrometers, I am not going to discuss these in detail. You were having these post-column spectrometers, and through different energy channels, after you do the energy filtering, you are allowing the signal to go through a specific window of the spectrometer, and then you are collecting the spectra. If you look at the modern day microscopes, either in column or post column energy filters, you have a kind of electrostatic and a magnetic prism which disperses the energy on. So once you are collecting the forward scattered electrons, you can disperse it on the energy window, and based on different energy filters that you are applying, which are sort of virtual filters, you can then start seeing within a specific energy window what kind of meaningful information you can get from EELS. So if I look at the energy filters, which are either magnetic prisms or electrostatic mirrors, you have the post column spectrometer, which is reasonably popular, which is available through most of the companies like Gatan or now COs as well. Or you have the in column filters, which is called as the omega filter, which is available either on the Zeiss or Joule TEMs. You are allowing the electron beam to go through this kind of an energy filter system, and you are dispersing the forward scattered inelastic electrons as shown on the previous slide on an energy window. And what happens is, on the x-axis you get the energy signature, and on the y-axis you are getting the number of counts of electrons that have undergone inelastic scattering at a specific energy. So if I look at how these spectra or images are obtained, you are collecting the signal from the direct beam either in imaging mode or in diffraction mode. When I am typically imaging in STEM, I am already operating in diffraction mode, but when I am imaging in conventional TEM, you can get spot EELS spectra. I go to a specific region and I place my specimen of interest or my field of view of interest aligned with the entrance aperture of the post column imaging filter. Typically, depending on whichever system you are looking at, you have on the fluorescent screen camera some kind of a signal like this, and somewhere around this region of your centralmost spot, you typically have an entrance aperture which is either 2 mm or 5 mm or in some cases 10 mm, and you want to align your feature of interest to coincide with this region on your fluorescent screen, and within a very small angle of deviation you have both the elastic and inelastically scattered electrons which are allowed to go through the entrance aperture, and then this goes through the magnetic prism, and then you start dispersing the electrons on a dispersion plane of different energies. And to give you an example of how the post column EELS system or the energy filter looks like is, you have a sort of a differential pumping aperture. You have this and you have an entrance aperture of 2 or 5 millimeter like I was mentioning. So once the forward scattered electron goes through the entrance aperture, you are collecting this either at the diffraction plane, and you have a series of the photodiodes, or nowadays we have the CCD camera, and once it passes through the prism which is kind of oriented at this 90 degrees here, it is typically a magnetic prism. You are now scattering the, or you are now dispersing the inelastically scattered electrons as a function of energy here, and this is what is recorded on either your CCD camera or in the old days they were the photodiode arrays, and from each of this pixel or each of this channels of the array that you have, you get certain number of electrons passing through, and you can get meaningful information on how many electrons corresponding to which energy are actually being collected. And from this, of course, you start getting quantitative information from the ionization edges. So if I look at what is done to obtain EELS spectrum is, typically on your spectrometer, if I am looking at something called as the fast scan camera, you can look at how the spectrum image is before I correct the spectrometer. There are a series of electromagnetic lenses also in the spectrometer. Typically, you see this kind of a shape. So you have different kinds of corrections. You have the coma and the magnetic field compensation which is done. Please bear in mind that electron energy loss spectroscopy is extremely sensitive to the stray electromagnetic fields. So ensure that there are not many stray electromagnetic fields or these are corrected. And typically what we do in EELS is, we first see this kind of a spectrum. This is typically your low loss or your zero loss peak, and if you have a thicker specimen, you see a shadow signature of the plasmon peaks as well. And looking at the zero loss peak, nowadays this compensation and correction is automated, but in the olden days we were doing it by enabling the multifunction knobs to correct for the spectrometer, and we were looking at the shape of these zero loss peaks and ensure that you have a very narrow zero loss peak. This is the image of the spectrum you are actually collecting on the spectrometer, and when I disperse it on the energy axis, this has to be aligned to be coinciding with the zero loss spectrum, and ensure that when I disperse this on the spectrometer, this appears more or less like a Gaussian peak with as narrow width as possible. So this is the first step that you do. So before you start obtaining the EELS information from a sample, you go to the vacuum region within the specimen, go to a hole, just look at how the zero loss peak looks like, and when there is no inelastic scattering and no interaction with the specimen, all the signal you will collect is of course the zero loss spectrum. So use this to correct for the spectrometer drift and the compensation through the magnetic coils to make it as narrow as possible and as ideal shaped as a Gaussian that you can get, and then bring in your sample and start collecting the low loss or the core loss information. So this is the first step that you need to do, no matter which way you're doing it, using which kind of a filter. So the first step is, of course, focusing of this spectrometer. We were simply calling it like a sharp wick. You make it as narrow as possible and make it, initially it is actually asymmetric, make it as symmetric as possible through the compensation coils. This is largely automated these days, but automation can lead you to a shape somewhat like this, largely to an extent. And once you come close to this, you can see that this can have somewhat funny shapes and you can have a kind of inclination of this at a certain angle. You correct for all these and then you look at the dispersion spectrum, and by changing at what kind of energy window you are looking at, you have different kinds of dispersion. You can have 0.01 eV per pixel or 0.1 eV or 0.3 eV. This gives you an idea of what kind of an energy range you are collecting the signal from, and then you decide whether you are looking at low loss or core loss spectra. So typically the energy filtering systems you have now, you have 1024 pixels, and this multiplied with this dispersion that you have gives you the energy window you are looking at. So for example, if I am looking at 0.01 eV per pixel multiplied with 1024 gives me 10.24 eV window of energy that I am collecting, and this is what you get for the EELS low loss spectra. With 0.1 eV I am looking at 102 eV window, and this gives me the bulk plasmon and some of the low loss energy events only. So this is how you start tuning your spectrometer and start obtaining data in EELS. So a few important steps again before obtaining EELS spectra is, you have to calibrate the spectrometer based on all the changes that happen in the environment of the electron microscope room that you have, and whatever stray electromagnetic signals you get, you always have to tune the imaging filter. When I call it as GIF, this is referring to what I learnt on the Gatan imaging filter system. This is also called as tuning the isochromaticity of the energy filter system now of the so-called CEFID EELS system as well. So you have to align the zero loss peak. So the first step is ensure that the dispersion plane of the spectrometer is as achromatic as possible, or make it as isochromatic surface as possible. Because these are largely CCD or CMOS kind of cameras that are now used, depending on which energy window you are recording on, you can have some saturation, and while you are recording the data from the previous user, the dispersion plane that you are recording on the CCD camera can also have stray signal which leads to some achromacity also. So you should correct for this. So that is why the first step would be to tune the image filtering system to get as isochromatic surface as possible. Then you align the zero loss peak. So you have to make the zero loss peak coincide with 0 on the dispersion plane, and then you have to get the optimum spectrometer resolution. This is what I talked on the previous image, where you see the funny shapes of the EELS spectrum which can appear like this, or in a very good case like a narrow line. With the appropriate dispersions, you see that you can get the best energy resolution of the zero loss peak. Here is an example of a field emission gun. I think this was obtained on a Techni coupled with a Schottky FEG. We were able to obtain 0.4 eV energy resolution on this particular condition of that particular microscope operated at 200 eV. Do you think this zero loss peak is well aligned? If you check if I draw a straight line here from 0, there is a small shift in the zero loss peak. It is a very small shift. Even if it is under 1 EV of misalignment, what happens is, suppose I am tuning my spectrometer with this kind of an alignment. Later I am recording, for example, oxygen spectra. The peak that should start at 531 EV might actually drift a little bit, and it may start from 530 EV. So, a good practice to record accurate EELS data is, with the illumination conditions that you are actually obtaining the data, you collect the zero loss peak first, get your core loss spectra. After you record the core loss image, again record a zero loss spectra again to check if there is any drift in the zero loss peak. Quite often while you are imaging as well, because there are a lot of electromagnetic components within the microscope as well, there is a good chance that the spectrometer can also drift a little bit. So, once you compensate for these, the data that you collect can be corrected for the drift as well, and you can get accurate EELS information. So, these are a few points that you need to bear in mind regarding the alignment of EELS spectrometer to get good quality data. So, the other necessary parameters are, so here is an image which I flipped around because this aligns with how the spectrometer is positioned within the microscope column. You have the incident beam, you have the convergent angle. If I am imaging in STEM mode, the convergence angle alpha is actually fixed depending on what kind of condenser aperture I am using. Even if I am doing it with a microprobe or a conventional TEM image, based on the condenser aperture I use and based on the area of illumination I am having, this is kind of fixed. Your convergence angle is fixed, and the brightness and the current densities that your incident electron beam is incident on the specimen is something which you also need to record and have it for quantitative EELS measurements as well. The next parameter is the thickness of the specimen. This you would already measure with your low loss EELS spectra. And then what you have is, based on the entrance aperture, whether I am using 2 mm or 5 mm, my collection angle is also fixed. Nowadays, the quantitative EELS measurements based on certain mathematical equations similar to the Rutherford elastic scattering, you also have EELS inelastic scattering information, and there is a lot Kramer-Kronig analysis and so on. I will not go into the mathematical details of that, but this parameter of the collection angle is also extremely important to get quantitative EELS data. So, please bear in mind that from one set of data that I collect from a sample, all these parameters are fixed and you note them down carefully, and you use the same set of parameters for one set of study that you do. Once you optimize on which kind of exposure times, illumination conditions, collection conditions I get the best EELS spectra, you standardize this and then you start recording the data from series of your specimens. So, once you do all this, I would like to pose a question here again. For best quantitative EELS study, actually STEM mode is more reliable. Can you think of it and answer why? I have already told this and discussed this while I was talking about STEM imaging, and I kind of gave you a few hints on how to fix the parameters. The answer is very simple. When I have STEM imaging and when I make a probe, at least my illumination parameters are consistent and fixed. If I am imaging in conventional TEM mode, there is no guarantee that I actually can have exactly the same illumination parameters for two different regions within the same specimen, or once I remove the specimen and load the specimen again, if I get the same kind of beam currents. if I pay attention to the brightness and the current densities and the convergence angles and the illumination conditions consistently with different specimens and different regions of the specimen, then I can be sure that even in conventional TEM, I can do quantitative yields. Initially, combination of conventional TEM plus diffraction mode was what primarily the yields kind of studies were done, and with the advent of STEM techniques, it became a lot more reliable. So that is why when you're doing STEM imaging combined with yields, this is called as STEM yield spectrum imaging. This is more and more popular these days to do quantitative yield studies. So the instrumentation parameters that are related to yields and that can give rise to problem are, in CCD array, like I was mentioning, you can have ghost peaks due to oversaturation. So that is why the first step of normalizing the intensity at the dispersion plane is very important. In the old days, you had photodiode arrays which were used for spectrometers. You have a larger dark current with the CCD detectors. So depending on how easy or how your yield spectrometers are, it doesn't harm in correcting and normalizing the intensities after every session or at least once in a day, and tuning the energy filter system. It is important before you run every yields measurement, and it is extremely sensitive to stray electromagnetic fields. If I do all this and if I start collecting the yields data, when I use the imaging filters, you can also get energy filtered TEM images which appear like this. I look at the yields core loss details. This is an unfiltered bright field image. Here is an example from an aluminum sample with copper precipitates. If I look at the yields energy loss spectra from copper L23 edge, what you are doing is you are getting a pre-edge window and a post-edge window, and from this I am trying to collect information only within this window for a 40-second exposure, and by doing this I can actually get compositional maps which is called as energy filtered TEM as well. So unlike the spectral imaging where I can get from each pixel a corresponding energy loss spectra, I can also get energy filtered TEM imaging, and typically the spatial resolution of this depending on which energy window I am looking at. So if I am looking at only the zero loss or the low loss spectra, I can even reach atomic resolution imaging with yields as well. That is when I am looking at only the elastically scattered electrons. But with low loss to up to 100 EV window, I can have a spatial resolution of somewhat around 1 nanometer. But as I go higher, 500 to 1000 EV, this spatial resolution of the compositional maps I get can drop down to 2 to 5 nanometer as well. So this is a broad overview on what yields is and what inelastic scattered electrons can actually give you, and how the spectra and images you collect can help you in getting analytical information from a sample. So I'll end this lecture here. In the next lectures, we'll start seeing how the construction of the spectrometer is and some examples of how the quantitative yields data is.